Okay, welcome back. Gas laws. So STP conditions and Dalton's law. Okay. First of all, back to the STP conditions thing. All right, what do they mean by STP conditions? Well, STP stands for standardized temperature and pressure. So we could put, little dots there if we wanted to. We don't. So why is there a standard temperature and pressure? Well, we go back to the beginning of the year about standardized units. If we're going to exchange data from one lab to another or one country to another, then we have to be using the same type of conditions. And with gases, slight changes in temperature and pressure gives you very different results. So if we were to run a lab on a hot day, air conditioning's broke, we're going to get very different results than on a cold day if the heat is broken in our lab. Apparently we work in a terrible lab where our heating and air conditioning doesn't work. So they decided, well, you do your lab, you get your result, and then you convert it to what's called STP conditions. So the standardized temperature is 0 Celsius, and the standard pressure is 1 atmosphere. And of course, we would measure it in Kelvin, so 273 Kelvin and 760 millimeters of mercury. They like to give you these type of initial and final state problems where you use what's called the combined gas law. So let's try this one. Okay, so I'm doing this problem and I'm saying, all right, well, it's an initial final state problem. How do I know? It says so right in the title. But they want a volume, and they're giving me an initial volume and a final volume, so I know volume has to wind up in my equation. And they're saying, all right, we're giving you a pressure initially. So here's my P1. Well, what's my P2? Well, P2 is my STP conditions. That's actually P2, the standard pressure. And temperature, again, 25 degrees Celsius. So we're converting it to a new temperature, so there's my T2. So I need pressure, volume, and temperature in the same equation. They're not changing the number of moles of gas. So we can do P1 V1 over T1 equals P2 V2 over T2, where our new conditions are going to be our STP conditions. Okay. So they want us to calculate a new volume, so we're going to solve for V2. So V2 is going to be a little algebra here. And now I can substitute in. My initial pressure was given to me in kilopascal, so I'll just keep it kilopascal. They're not asking me to change it. And my initial volume, milliliters, so I can answer in milliliters. Now, T2 is standard temperature. So standard temperature, and again, we're going to use Kelvin because that's what the gas laws are designed for, so I'm going to do 273 Kelvin. And my second pressure is standard pressure, which is 101.325 kilopascal. And my initial temperature is 25 degrees C, so I'm going to have to do a little conversion here. Kelvin is equal to degrees C plus 273. So I'll take my 25 degrees C, add it to 273, and my kelvins are 298 K. So I'll substitute that in there. And now it's just a matter of little calculator work. 321.4 times 500 times 273 divided by 101.325 divided by 298. And I get 1,452.933, and how many sig figs? 3 sig figs, so 1,450 milliliters. Now, usually on a multiple choice test, you'll see that converted to liters, so the answer on multiple choice would probably be 1.45 liters. But if it's a free response question, they don't ask you to convert it to liters, then you certainly don't have to. And again, the only trick to this problem is recognizing that your STP conditions were your new temperature and your new pressure. Okay, second topic. Dalton's law of partial pressures. So Dalton's law says that when you have a mixture of gases, the total pressure in the container is equal to the partial pressures that are created by each of the individual gases. And here's the equation for it. P total is equal to partial pressure of gas A plus partial pressure of gas B plus partial pressure of gas C. All right, so what do we mean by partial pressure? First of all, partial pressure would be, hey, let's say your gas makes up 50% of the particles in your mixture. Well, then it's also going to create 50% of the pressure under ideal conditions, because we said it wasn't the identity of the particles that matter. It's the number of particles and the force that hits on the side of the container wall. So since they all share the same thermal environment, they all have the same kinetic energy. So therefore, we are dealing with, if a particle is more massive, it has less velocity, but it still has the same amount of kinetic energy. Therefore, it's creating the same force when the particle hits the container wall. So it's really the number of particles that determines its partial pressure, and you can treat those gases as though they're acting independently. So if we know their partial pressures, then we can add them up to get total pressure. Or if we know the total pressure, we can solve for the partial pressure. And if we know the partial pressure at the higher level at AP, then we can start to calculate the moles of that gas and then use it to make some other calculations. So here's an example I stole from the internet. The Earth's atmosphere, primarily these 5 gases, oxygen, nitrogen, argon, water vapor, and carbon dioxide, makes up what we would call air. And they didn't have the units here, but these values represent percentages. So oxygen, for instance, would be 20.9% of the Earth's atmosphere. Nitrogen would be 78.1%. So if you add up all these percentages, you get 100% total. So let's say that we had a total pressure of 1 atmosphere. That means that oxygen would be 0.209 atmospheres, nitrogen would be 0.781 atmospheres, argon would be 0.97, etc., etc. We add up the other 2 values. Oh, I'm sorry, not 0.97, 0.097, and then 0.128, and then carbon dioxide makes up 0.05%, and that would give us a total of 1 atmosphere total pressure. So that would be one easy problem. If they said, hey, nitrogen is 75% and argon is 12%, then, what percentage of the mixture those two are? I'm sorry. That's really a terrible question. I mean, if they give you the partial pressure of each of those gases, you just add them up to get the total pressure. Here's another example. Suppose we have this gas in container A, this green gas, and it has a total of 4 particles. And the gas in container B is a total of 10 particles. And container C, these are diatomic, so they're actually 1 particle when you put 2 of them together. So that's a total of 8 particles. Of course, when we put them together in the same container, we're going to have 22 particles. So that means that if container A had a pressure of 4 atmospheres, well, actually, we can just read the pressures off of the example. I'm sorry. If the first one is 100 kilopascal, and the second one is 250, third one's 200, then they're going to add up to equal 550 kilopascal. But the same ratios. 100 to 550 is the same as 4 particles to 22. 250 kilopascal for the second one would be the same as 10 out of 22 for the total container. It would be the same percentage. So again, an easy application of Dalton's law. What's impractical about this, other than atmospheric mixtures, is the idea of taking 3 separate containers of gas, pumping them out, and then pumping them into one container that happens to be the exact same size as the other 3 containers. That's very unlikely to happen. When you have gas mixtures, usually what you get is something like this. You have 2 containers that are connected to each other by a valve. And you open up the valve, and we said that once you open up the valve, gas is spread out to fill their container. So let's say that this first container with the hydrogen is 1 liter, and the one with the oxygen in it is 1 liter. The oxygen spreads out into both containers. So the new container size for the oxygen, once you open up the valve, is not 1 liter. It's both of those containers together. You're now looking at a 2 liter total container. So what happens to the pressure of the oxygen when you open up the valve and let it spread out? Well, the more space you have, the more the pressure drops, according to Boyle's law. So we really have a P1V1 equals P2V2 situation here, where P1V1 is the condition of the gases before we open up the valve, and P2V2 would be the condition of the gases after we open up the valve. Okay, so who cares? Here's why we care. This is more likely the type of Dalton's law problem you would get rather than just adding up the values for the pressures. In this one, argon's in a very large container. Hydrogen's in a very small container. So when you open up the valve, the hydrogen container is no longer 1 liter. It's going to spread out into the other 2 containers. And so the hydrogen goes from a container size of 1 liter to 1.5 plus 1 plus 2. So a total of 4.5 liters. And its pressure drops dramatically. So it goes from 1 liter to 4.5 liters. Oopsie poopsie. So its new container size 4.5 liters. Well, the same thing happens to carbon dioxide. Its new container will also be 4.5 liters. Argon will be 4.5 liters. But the difference is the hydrogen is going through a much larger dramatic increase in volume for its container. It's going from 1 to 4.5. It's increasing its size of its container by 450%. Where the argon container is going from 2 liters to 4.5, it's a little bit more than double. So the argon pressure isn't going to drop as dramatically as the hydrogen pressure is. So on a Dalton's law problem, you're really applying 2 things here. As they open up the valve and the gases mix, the pressures for each of the gases individually drop. You have to figure out how much that pressure drops before you add them together. And I'll show you how to do that. Okay. All right, so first of all, we know that our new container size is going to be the addition of all these together. So we're going to have, let's call this V2, our new volume, is going to be the 1.5 liters from the first container, the red container, to the light blue. And then we're also going to add the gray container, which is 2.00 liters. So we get 4.50 liters. Pardon me. So before we get the total pressure, we really have to make an adjustment. We need P2 for the carbon dioxide, and P2 for the hydrogen, and P2 for the argon. We need the new pressures after you open the valve. So here's how you calculate them. Do each one and apply Boyle's law. So you do P1V1 equals P2V2, and then you solve for P2. Now you only have to write, if it's free response, you only have to write the equation once and solve it. So we're going to substitute in for each of those 3 gases. Let's start with carbon dioxide. All right, so for carbon dioxide, our new pressure is going to be our initial pressure, our initial volume, and our new volume. So this comes out to be 2.13 times 1.5 divided by 4.5. You get 0.71. We've got to do 3 sig figs here. So 0.710 atmospheres. So that's the new pressure for carbon dioxide. And by analogy, we're going to do the same thing for the other 2 gases. So for hydrogen, we're going to do 0.861. Its original container was 1 liter. We open up the valve. The new container is now 4.5. So that gives us a new partial pressure for hydrogen. So 0.861 times 1 divided by 4.5, we get 0.191. And then we're going to do, finally, the same thing for argon. The new pressure for argon, its original container, 2 liters, and divide that by 4.50 liters. So yeah, when we open up that valve, all the pressures do drop, but they don't drop equally, and we have to account for that before we add them together. Okay, so now we can finally add them together. So our total pressure is carbon dioxide plus hydrogen plus argon. And I get a total of 1.412. I say, wait a minute, can't be 4 sig figs, and I'm saying, yes, it can. Remember, the addition rule goes by the number of decimal places that you have, and each of these has 3 decimal places, so our final value also has to have 3 decimal places, so 1.412 atmospheres. Another type of Dalton's law problem is that when you're running chemical reactions, it's a shame we can't do the labs for this chapter because they're awesome. We actually run a lab like this. I use magnesium and hydrochloric acid. We hook it up to a tube. In order to collect gases safely, what you do is what's called water displacement. You fill a container, we would fill a burette with water, and then you run the tube into the burette, and then as the gas is produced, in this case hydrogen gas, it bubbles out the water and pushes the water out of the tube. And depending upon how much water gets pushed out, we can use the burette to calculate the volume of the hydrogen that's produced. The problem is this: what happens on the surface of that water when 2 fast-moving liquid water particles hit each other? Is there enough energy for them to hit each other with such force that they bounce off of the liquid surface and vaporize and evaporate? And the answer is yeah. So as you're displacing your hydrogen through the water bath, some of the water evaporates into your container, so you don't collect hydrogen, you collect hydrogen and water vapor, what they call wet gas, which I think is hysterical. And generally there are things that you can do to dry that gas out. You put it into what's called a desiccator. You ever buy shoes and they have those pouches in them that keep them dry? It's the same sort of thing. It's a material that absorbs water. Okay. Here's another example of it. You run your reaction, the gas bubbles through into the water sample and pushes the water out. But you pick up evaporated water in the process. So when you hook up a pressure gauge to it, that's not the pressure of your gas, it's actually a total pressure, which represents the pressure of the gas that you're trying to collect, plus the evaporated water. So you have to do your calculations based upon subtracting out the evaporated water. Now do understand that how much water evaporates is based upon the size of the container. But we're not looking at how much water evaporates in the process. What we're looking at is the pressure that it produces, and the pressure it produces is solely based on the temperature. If you have a very small container and you run your reaction at 20 degrees Celsius, then it's going to produce 17.5 millimeters of evaporated water in the container. Now, if it's a small container, it only takes a little bit of water to create the 17.5 millimeters of mercury. But if it's a large container, you get much more evaporated water, but it still produces a pressure of 17.5. The pressure that's created, what's called vapor pressure, is solely based on the temperature. All right, so what kind of questions do you get? All right, here's one. We're going to collect gas in a lab in a 250 milliliter burette at 295 K. And we hook up a pressure gauge and we get a pressure of 746.3 torr. What is the volume of the dry gas at STP? Good question. Okay, so first thing I need is, what is the vapor pressure at 295 K? Well, 295 K minus 273 gives me a temperature of 22 degrees Celsius. So we go back to our chart, and the water vapor pressure is 19.3 millimeters of mercury. Now, they would either give you that value on the problem, or they would give you a chart to look up that value. All right, so there we go. And that is the wrong slide. For shame. Okay, there we go. All right, so first of all, the pressure of the water that evaporates during the collection, we said was 19.3 millimeters of mercury, which is the same as 19.3 torr. Okay, so before we do anything with this problem, we have to figure out what is the pressure of the dry gas, and I'm just going to call it pressure dry. Well, first of all, total pressure is going to be equal to the partial pressure of the dry gas plus the partial pressure of the evaporated water. So we can solve for the dry gas. All right, so what's our dry gas pressure? Total pressure was 746.3 torr, and we're going to subtract 19.3 torr. So that's going to give us 727.0 torr. Let's call that V1. Or I'm sorry, P1 rather. Let's call that P1. That's our pressure that we're starting with. So we're not dealing with this pressure. I mean, we need the 746.3, but that's not the pressure of our dry gas. That's the pressure of the dry gas contaminated with the evaporated water. So we subtract out the water vapor pressure, and we're really starting with a pressure of 727 torr. So that gives us a P1. We already have a V1. Here's our T1. And if they're asking us to solve for a new volume, and our new volume is V2, and STP, that means new temperature. T2, new pressure, P2. STP conditions. So this is just another combined gas law problem at that point. So we're going to solve it as such. All right, so we'll go P1, which is actually pressure of the dry gas, V1 over T1 equals P2 V2 over T2. Remember, our P2 and our T2 are our STP conditions. Let's solve for V2. And now we can just substitute in. It's a pretty easy problem from here. Again, the secret, subtracting out the evaporated water. And our new temperature is STP, which is 0 Celsius, or 273 K. We're not going to use Celsius because you don't use Celsius in gas laws. We got to keep everything in the first quadrant. It's got to be positive values. Celsius has negative values. All right, V2. Oh, I am a fool. I'm supposed to solve for V2, so that should be P2 there. Why do you folks let me do stuff like that? Somebody should have stopped me. All right, so P2 is the new pressure, which is standard pressure, which is 760 torr. And T1 was our original temperature at 295 K. All right. Let us solve. 727 times 250 times 273 divided by 760 divided by 295. I get a new volume of 221.31 blah 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 milliliters. So we're just going to do 3 sig figs. 221 milliliters. So we would run this experiment at 295 K, so 22 degrees Celsius, about 74 degrees Fahrenheit, and we would get a pressure of our dry gas at 727 torr and a volume of 250 milliliters. We fill the container. However, slight differences in temperature, right? At STP, we run the same experiment, and our container would only be it would only fill at 200. Oh, I shouldn't say it this way. In order to get the same standard pressure, we'd have to have a container of 221 milliliters. 250 wouldn't do it. So again, slight changes in temperature and pressure make a big difference. So therefore, a lot of times they ask us to give our results in STP. Okay. There's one more type of Dalton's problem. There is Graham's law, and then that's it for chapter 18. And then I'm going to go through and do a bunch of practice problems. So we'll finish up Dalton's law in part 3. We'll do Graham's law in part 3, and then I'll do practice problems in part 4. All right. Thank you very much.